Aircraft performance. This lesson will discuss the factors that affect aircraft performance, which include the aircraft weight, atmospheric conditions, runway environment, and the fundamental physical laws governing the forces acting on an aircraft. The Performance or Operational Information section of the Aircraft Flight Manual Pilot's Operating Handbook contains the operating data for the aircraft. That is, the data pertaining to takeoff, climb, range, endurance, descent, and landing. The use of this data in flying operations is mandatory for safe and efficient operation. Considerable knowledge and familiarity of the aircraft can be gained through study of this material. Since the characteristics of the atmosphere have a major effect on performance, it is necessary to review two dominant factors: pressure and temperature. The atmosphere is an envelope of air that surrounds the Earth and rests upon its surface. It has mass, weight, and indefinite shape. Air, like any other fluid, is able to flow and change its shape when subjected to even minute pressures because of a lack of strong molecular cohesion. Though there are various kinds of pressure, pilots are mainly concerned with atmospheric pressure. It's one of the basic factors in weather changes, helps to lift the aircraft, and actuates some of the most important flight instruments in the aircraft. These instruments often include the altimeter, the airspeed indicator, the vertical speed indicator, and the manifold pressure gauge. The density of air has significant effects on the aircraft's performance. As air becomes less dense, it reduces power because the engine takes in less air, thrust because the propeller is less efficient in thin air, and lift because the thin air exerts less force on the airfoils. The pressure of the atmosphere varies with time and altitude. Due to the changing atmospheric pressure, a standard reference was developed. The standard atmosphere at sea level is a surface temperature of 59 degrees Fahrenheit or 15 degrees Celsius and a surface pressure of 29.92 inches of mercury or 1013.2 millibars. A standard temperature lapse rate is one in which the temperature decreases at the rate of approximately 3.5 degrees Fahrenheit or 2 degrees Celsius per 1,000 feet. A standard pressure lapse rate is one in which pressure decreases at a rate of approximately 1 inch of mercury per 1,000 feet of altitude gain to 10,000 feet. Any temperature or pressure that differs from the standard lapse rates is considered non-standard temperature and pressure. Adjustments for non-standard temperatures and pressures are provided on the manufacturer's performance charts. Since all aircraft performance is compared and evaluated with respect to the standard atmosphere, all aircraft instruments are calibrated for the standard atmosphere. Thus, certain corrections must apply to the instrumentation, as well as the aircraft performance, if the actual operating conditions do not fit the standard atmosphere. In order to account properly for the non-standard atmosphere, certain related terms must be defined. Pressure altitude is the height above the standard datum plane, SDP. The aircraft altimeter is essentially a sensitive barometer calibrated to indicate altitude in the standard atmosphere. If the altimeter is set for 2992 inches of mercury SDP, the altitude indicated is the pressure altitude, the altitude in the standard atmosphere corresponding to the sensed pressure. The SDP is a theoretical level where the pressure of the atmosphere is 2992 inches. As atmospheric pressure changes, the SDP may be below, at, or above sea level. Pressure altitude is important as a basis for determining aircraft performance, as well as for assigning flight levels to aircraft operating at above 18,000 feet. The pressure altitude can be determined by either of two methods. One, by setting the barometric scale of the altimeter to 2992 inches and reading the indicated altitude, or two, by applying a correction factor to the indicated altitude according to the reported altimeter setting. The more appropriate term for correlating aerodynamic performance in a non-standard atmosphere is density altitude. The altitude in the standard atmosphere corresponding to a particular value of air density. Density altitude is pressure altitude corrected for non-standard temperature. As the density of the air increases, lower density altitude, aircraft performance increases. Conversely, as air density decreases, a higher density altitude, aircraft performance decreases. A decrease in air density means a high density altitude. An increase in air density means a lower density altitude. Density altitude is used in calculating aircraft performance. Density altitude is determined by first finding pressure altitude and then correcting this altitude for non-standard temperature variations. Since density varies directly with pressure and inversely with temperature, a given pressure altitude may exist for a wide range of temperature by allowing the density to vary. However, a known density occurs for any one temperature and pressure altitude. The density of the air, of course, has a pronounced effect on aircraft and engine performance. Regardless of the actual altitude at which the aircraft is operating, it will perform as though it were operating at an altitude equal to the existing density altitude. Air density is affected by changes in altitude, temperature, and humidity. High density altitude refers to thin air, while low-density altitude refers to dense air. The conditions that result in a high-density altitude are high elevations, low atmospheric pressures, high temperatures, high humidity, or some combination of these factors. Lower elevations, high atmospheric pressure, low temperatures, and low humidity are more indicative of low-density altitude. Using a flight computer, density altitude can be computed by inputting the pressure altitude and outside air temperature at flight level. Density altitude can also be determined by referring to the table and chart shown here. Performance is a term used to describe the ability of an aircraft to accomplish certain things that make it useful for certain purposes. For example, the ability of an aircraft to land and take off in a very short distance is an important factor to the pilot who operates in and out of short, unimproved airfields. The primary factors most affected by performance are the takeoff and landing distance, rate of climb, ceiling, payload, range, speed, maneuverability, stability, and fuel economy. Some of these factors are often directly opposed. For example, high speed versus short landing distance, long range versus great payload, and high rate of climb versus fuel economy. It is the preeminence of one or more of these factors that dictates differences between aircraft and explains the high degree of specialization found in modern aircraft. All of the principal components of flight performance involve steady-state flight conditions and equilibrium of the aircraft. For the aircraft to remain in steady, level flight, equilibrium must be obtained by a lift equal to the aircraft weight and a power plant thrust equal to the aircraft drag. Thus, the aircraft drag defines the thrust required to maintain steady level flight. As presented in Chapter 4, Aerodynamics of Flight, all parts of an aircraft contribute to the drag, either induced or parasitic drag. While the parasite drag predominates at high speed, induced drag predominates at low speed. For example, if an aircraft in a steady flight condition at 100 knots is then accelerated to 200 knots, the parasite drag becomes 4 times as great, but the power required to overcome that drag is 8 times the original value. The maximum level flight speed for the aircraft will be obtained when the power or thrust required equals the maximum power or thrust available from the power plant. Climb performance is a result of using the aircraft's potential energy provided by one or a combination of 2 factors. The first is the use of excess power above that required for level flight. An aircraft equipped with an engine capable of 200 horsepower at a given altitude but using 130 horsepower to sustain level flight at a given airspeed has 70 excess horsepower available for climbing. A second factor is that the aircraft can trade off its kinetic energy and increase its potential energy by reducing its airspeed. The reduction in airspeed will increase the aircraft's potential energy, thereby also making the aircraft climb. Both terms, power and thrust, are often used in aircraft performance. However, they should not be confused. The most immediate interest in the climb angle performance involves obstacle clearance. The most obvious purpose for which it might be used is to clear obstacles when climbing out of short or confined airports. The maximum angle of climb would occur where there exists the greatest difference between thrust available and thrust required. For example, for the propeller-powered airplane, the maximum excess thrust and angle of climb will occur at some speed just above the stall speed. Thus, if it is necessary to clear an obstacle after takeoff, the propeller-powered airplane will attain maximum angle of climb at an airspeed close to, if not at, the takeoff speed. Range performance. The ability of an aircraft to convert fuel energy into flying distance is one of the most important items of aircraft performance. In flying operations, the problem of efficient range operation of an aircraft appears in two general forms. One, to extract the maximum flying distance from a given fuel load, and two, to fly a specified distance with a minimum expenditure of fuel. A common element for each of these operating problems is the specific range, that is, nautical miles, nm, of flying distance versus the amount of fuel consumed. Range must be clearly distinguished from the item of endurance. Range involves consideration of flying distance, while endurance involves consideration of flying time. If maximum endurance is desired, the flight condition must provide a minimum fuel flow. In this figure, at point A, the airspeed is low and fuel flow is high. This would occur during ground operations or when taking off and climbing. As airspeed is increased, power requirements decrease due to aerodynamic factors, and fuel flow decreases to point B. This is the point of maximum endurance. Beyond this point, increases in airspeed come at a cost. Airspeed increases require additional power, and fuel flow increases with additional power. The effect of altitude on the range of a propeller-driven aircraft is illustrated in this figure. A flight conducted at high altitude has a greater true airspeed, and the power required is proportionately greater than when conducted at sea level. The drag of the aircraft at altitude is the same as the drag at sea level, but a higher true airspeed causes a proportionately greater power required. The effect of altitude on specific range can also be appreciated from the previous relationships. If a change in altitude causes identical changes in speed and power required, the proportion of speed to power required would be unchanged. The fact implies that the specific range of a propeller-driven aircraft would be unaffected by altitude. Actually, this is true to the extent that specific fuel consumption and propeller efficiency are the principal factors that could cause a variation of specific range with altitude. Takeoff and landing performance. The majority of pilot-caused aircraft accidents occur during the takeoff and landing phase of flight. Because of this fact, the pilot must be familiar with all the variables that influence the takeoff and landing performance of an aircraft, and must strive for exacting professional procedures of operation during these phases of flight. The important factors of takeoff or landing performance are that takeoff or landing speed is generally a function of the stall speed or minimum flying speed. The rate of acceleration, deceleration, during the takeoff or landing roll. The speed, acceleration and deceleration, experienced by any object varies directly with the imbalance of force and inversely with the mass of the object. An airplane on the runway moving at 75 knots has 4 times the energy it has traveling at 37 knots. Thus, an airplane requires 4 times as much distance to stop as required at half the speed. The takeoff or landing roll distance is a function of both acceleration, deceleration, and speed. Runway surfaces vary widely from one airport to another. The runway surface encountered may be concrete, asphalt, gravel, dirt, or grass. The runway surface for a specific airport is noted in the Airport Facility Directory, AFD. Any surface that is not hard and smooth will increase the ground roll during takeoff. This is due to the inability of the tires to roll smoothly along the runway. Tires can sink into soft, grassy, or muddy runways. Potholes or other ruts in the pavement can be the cause of poor tire movement along the runway. Obstructions, such as mud, snow, or standing water, reduce the airplane's acceleration down the runway. Although muddy and wet surface conditions can reduce friction between the runway and the tires, they can also act as obstructions and reduce the landing distance. Braking effectiveness is another consideration when dealing with various runway types. The condition of the surface affects the braking ability of the aircraft. The gradient or slope of the runway is the amount of change in runway height over the length of the runway. The gradient is expressed as a percentage, such as a 3% gradient. This means that for every 100 feet of runway length, the runway height changes by 3 feet. A positive gradient indicates the runway height increases, and a negative gradient indicates the runway decreases in height. An upsloping runway impedes acceleration and results in a longer ground run during takeoff. However, landing on an upsloping runway typically reduces the landing roll. A downsloping runway aids in acceleration on takeoff, resulting in shorter takeoff distances. The opposite is true when landing, as landing on a downsloping runway increases landing distances. Runway slope information is contained in the AFD. Takeoff performance. The minimum takeoff distance is of primary interest in the operation of any aircraft because it defines the runway requirements. The minimum takeoff distance is obtained by taking off at some minimum safe speed that allows sufficient margin above stall and provides satisfactory control and initial rate of climb. To obtain minimum takeoff distance at the specified liftoff speed, the forces that act on the aircraft must provide the maximum acceleration during the takeoff roll. In addition to the important factors of proper procedures, many other variables affect the takeoff performance of an aircraft. Any item that alters the takeoff speed or acceleration rate during the takeoff roll will affect the takeoff distance. For example, the effect of gross weight on takeoff distance is significant, and proper consideration of this item must be made in predicting the aircraft's takeoff distance. If the gross weight increases, a greater speed is necessary to produce the greater lift necessary to get the aircraft airborne at the takeoff lift coefficient. The effect of wind on takeoff distance is large, and proper consideration also must be provided when predicting takeoff distance. The effect of a headwind is to allow the aircraft to reach the takeoff speed at a lower ground speed, while the effect of a tailwind is to require the aircraft to achieve a greater ground speed to attain the liftoff speed. The effect of proper takeoff speed is especially important when runway lengths and takeoff distances are critical. The takeoff speeds specified in the AFM-POH are generally the minimum safe speeds at which the aircraft can become airborne. Any attempt to take off below the recommended speed means that the aircraft could stall, be difficult to control, or have a very low initial rate of climb. In some cases, an excessive angle of attack may not allow the aircraft to climb out of ground effect. On the other hand, an excessive airspeed at takeoff may improve the initial rate of climb and feel of the aircraft, but it will produce an undesirable increase in takeoff distance. Assuming that the acceleration is essentially unaffected, the takeoff distance varies with the square of the takeoff velocity. The effect of pressure altitude and ambient temperature is to define the density altitude and its effect on takeoff performance. While subsequent corrections are appropriate for the effect of temperature on certain items of power plant performance, Density altitude defines specific effects on takeoff performance. An increase in density altitude can produce a twofold effect on takeoff performance: greater takeoff speed and decreased thrust and reduced net accelerating force. Proper accounting of pressure altitude and temperature is mandatory for accurate prediction of takeoff roll distance. The most critical conditions of takeoff performance are the result of some combination of high gross weight, altitude, temperature, and unfavorable wind. Landing performance. In many cases, the landing distance of an aircraft will define the runway requirements for flight operations. The minimum landing distance is obtained by landing at some minimum safe speed, which allows sufficient margin above stall and provides satisfactory control and capability for a go-around. A distinction should be made between the procedures for minimum landing distance and an ordinary landing roll with considerable excess runway available. Minimum landing distance will be obtained by creating a continuous peak deceleration of the aircraft. That is, extensive use of the brakes for maximum deceleration. On the other hand, an ordinary landing roll with considerable excess runway may allow extensive use of aerodynamic drag to minimize wear and tear on the tires and brakes. In addition to the important factors of proper procedures, many other variables affect the landing performance. Any item that alters the landing speed or deceleration rate during the landing roll will affect the landing distance. The effect of gross weight on landing distance is one of the principal items determining the landing distance. One effect of an increased gross weight is that a greater speed will be required to support the aircraft at the landing angle of attack and lift coefficient. When minimum landing distances are considered, braking friction forces predominate during the landing roll, and, for the majority of aircraft configurations, braking friction is the main source of deceleration. The effect of wind on landing distance is large and deserves proper consideration when predicting landing distance. Since the aircraft will land at a particular airspeed independent of the wind, the principal effect of wind on landing distance is the change in ground speed at which the aircraft touches down. The effect of wind on deceleration during the landing is identical to the effect on acceleration during takeoff. The effect of pressure altitude and ambient temperature is to define density altitude and its effect on landing performance. An increase in density altitude increases the landing speed, but does not alter the net retarding force. Thus, the aircraft at altitude lands at the same indicated airspeed as at sea level, but because of the reduced density, the true airspeed is greater. The most critical conditions of landing performance are combinations of high gross weight, high density altitude, performance charts. Performance charts allow a pilot to predict the takeoff, climb, cruise, and landing performance of an aircraft. These charts, provided by the manufacturer, are included in the AFM-POH. Information the manufacturer provides on these charts has been gathered from test flights conducted in a new aircraft under normal operating conditions while using average piloting skills and with the aircraft and engine in good working order. By using these performance charts, a pilot can determine the runway length needed to take off and land, the amount of fuel to be used during flight, and the time required to arrive at the destination. It is important to remember that the data from the charts will not be accurate if the aircraft is not in good working order or when operating under adverse conditions. Compute the performance of the aircraft prior to every flight, as every flight is different. Not all of the information on the charts is easily extracted. Some charts require interpolation to find the information for specific flight conditions. Interpolating information means that by taking the known information, a pilot can compute intermediate information. However, pilots sometimes round off values from the charts to a more conservative figure. Performance characteristics and capabilities vary greatly among aircraft. Moreover, aircraft weight, atmospheric conditions and external environmental factors can significantly affect aircraft performance. It is essential that a pilot become intimately familiar with the performance characteristics and capabilities of the aircraft being flown.